definition has the following form: P is RT by B minus B. Minus A times alpha of the pendulum. And then it has B squared plus 2BB minus B squared. So this we know how to, if you want to calculate the dV, certainly you will get RT log B minus B. Right? And if you are integrating from BL to BB, you get the same term. Because this integration is very straightforward. I will simply integrate this B squared plus 2BB minus. So I have to factor this out into two linear factors, right? And you can easily factorize it to solve the quadratic equation and find the roots. So the roots are, let's say, alpha and beta. So B minus alpha and B minus beta will be the two factors. Then you can write it as partial fractions, right? So I can write this as, let's say, alpha, beta are the roots of the equation B squared plus 2BB minus B squared equal to 0. Right? So I can split this as integral, or rather this factor alone, 1 over, it will be C1 by B minus alpha plus C2 by B minus beta. So you have to find C1 and C2. Only thing in the case of the SRK, the factors are obvious, B and B plus B, and you can also infer the coefficients quite easily. Here you have to maybe do a slightly, but the answer you will get is RT integral B into RT log BB minus B by BL minus B, and then minus A times alpha of T. Then you get 2 root 2b. This will come as coefficients. C1 and C2 will probably be the negative of each other. And then the logarithm, you will get two factors. One would be b corresponding to would be minus b times root 2 minus 1 divided by bb plus b times root 2 plus 1. And this would be multiplied by the corresponding factor for BL, which would be B times 1 plus root 2 by BL minus B into root 2 minus 1, something like that. Now this is also written in a slightly different form in many books in terms of the compressibility factor, because we know that Z is PV by RT. Because you are anyway solving in terms of Z that is recommended, not A. So you get the roots in terms of Z, ZB and ZL. So I can write this by multiplying both the numerator and denominator by P over RT. Right? So I can write this as ZB minus capital P, which we have already introduced as one of the coefficients of the cubic equation in terms of the compressibility factor. That is simply the small b times P over RT, right? So you can write it like that. It's probably a more convenient form. So if we take the units at one stage and then we are taking essentially the dimensionless quantities, that's the advantage of the same thing can be, probably even this can be written like that. I don't know, but anyway, we leave it like this. This can all be converted like a very straightforward manner. And so on. So you can complete what I want you to do is to verify that in fact the Fugacity ratios will be almost the same FV over FL when you, for the saturation pressure given 1.95 or something regardless. If you substitute it into this equation, you will certainly find the two terms are very much close to each other. What I mean is this whole term and then the P sat times PV minus BL, right? So you have to verify that. We can move on to the Fugacity calculation from heat tables, right? So we'll take up not the problem given in the assignment. The problem worked out in Sandler, anyway, the procedure is the same. And what he asks is to calculate the first part 1. He is given water. The steam tables are readily available. So he is water. And the temperature he is given is T1 is 300 degrees centigrade. And T1 is he is saying 8 megapascal. So you want the fugacity at this point, at this temperature and pressure, right? So before we proceed further, we need to identify what state it corresponds to, right? So we know the let's draw approximately the way the PV diagram at T1 equal to 300 degrees centigrade would look like for water. Let's sketch it, right? It is going to be similar to what we had earlier. We were able to loop and all that. All that is watered off. And so we know that at the saturation pressure, there will be a transition, right? T1 equal to 300 degrees centigrade. First, we want to identify what where this is. Is it here or here or here? Right? So what you would first find from the table? The saturation pressure at 300 degrees centigrade. So there's a whole, you should be comfortable with using these tables. You will see two sets of tables, you might recollect, because you might have all used the three tables extensively. One is the saturated and another is superheated. We want to first know which one to look at. Right? So first, obviously, I want to fix the state, because we know the saturation pressure. The pressure is equal to the saturation pressure 8 megapascal. Then it will be either a liquid or a vapor. It could be either. But we don't care, because the fugacity of both liquid and vapor are the same, right? But if it is saturation pressure is greater than 8, then obviously it's going to be somewhere here in the gas state. The saturation pressure is less than 8, then it's going to be the liquid state. So that is why we have all even earlier seen for fixing the state, the calculation of saturation pressure is of utmost importance. But now we don't have to calculate it, we just look at the table and find out. So let's look at that, and I have the tables from, I think, Ravi Smith and Manus here. I'll put this up, and I don't know how quick, how much you can read this. I'll try to focus it. Probably not that clear. We might have to switch off the lights. Dust. What? Dust is there on this. Dust is there on this. Oh God. Certainly better now. So this is what we have, saturated steam tables. And you have to first understand what is given here. T equal to 300 is right at the top. If you see. It's okay, I will manage. T equal to 300, you can see, it's right at the top of the table. You might not be able to see it clearly, but I can read out the values, saturation pressure that is there right at the top. If we move this a little bit. Yeah, now maybe you can see here. The saturation pressure is in kilopascal 8592.7. I hope you can read, at least some of you can read. 8592.7. This is the 300 degrees centigrade given in Kelvin, and you have all the properties, the volumes, the vapor and liquid saturated. So this is purely saturated. Enthalpy, everything you get, right? So now let us see 8592 is 8.6 megapascal. right? So what do you think of the state that is given? Right? It is gas, actually it's called superheated vapor, right? So it's the gas states basically. So where would it be? It would be on this or this third one, right? So I can now mark this. This is 8.6 megapascal. So clearly 8 megapascal is somewhere here. So now we have verified that this is a superheated, because in the terminology of the tables, rather than saying it's gas, you have to call it a superheated vapor. Because now you have to go to the superheated vapor to calculate the fugacity. Now Sandler asked for two methods to calculate the fugacity. One, he says using volumetric data. Another, he says energetic data. Volumetric data was energetic data. So two methods are there. Given the tables, you can actually calculate the fugacity using two different methods. Now, if you look at the formula for fugacity, or rather the chemical potential departure function that we have, it is you can read it. I don't expect you to remember, but you can easily write it from one of the assignment sheets. Read this. So probably the longest formula among all the departure functions. That's all possible. The integral and then a logical term and then PV minus RT term. Right? It has everything. So now, if I want to write it in terms of an integral over P, how would it look like? We have seen the general formula for any property. If I want to express a departure function, it's integral du by dp minus du ig by dp integrated from 0 to the required pressure at a given temperature. So what is du by dp? You should know this by now. du, what is du equal to? So minus SdG plus vdp. So du by dp is b. B6 you cannot have. So B, of course, the temperature is T1 minus what? Corresponding quantity for the ideal gas. RT1 by P, not just any RT, but RT1. You can see the striking simplicity of this expression, right? Over this. This is what you get if you start from this and then integrate, use integration by parts and so on, you get all these terms. But you can very clearly see the departure function for the chemical potential, which is in turn directly related to the fugacity, right, is nothing but an integral of the departure of the volume. It's actually d minus dig integrated over p. Such a simple expression, very easy to remember for the departure function for the chemical potential. You should keep that in mind. Now this is what he wants you to use to calculate the fugacity. So the P1 is given now 8 megapascal, T1 is given 300. So we have to go to the superheated tables. For 300, superheated will both be in terms of pressure as well as temperature. You have to go to the 300 degrees centigrade superheated table and calculate actually RT1 by P is very easy. P over the entire range from 0 to 8. Now obviously we can't get the value at 0, it is obviously RT by P. But what pressure you would choose would depend on the lowest pressure available in the tables. Superheated will start from, this is the superheated state at 300. It is not only at 8 mega, it extends all the way down. That's what we want. We want the volume information for all of these states, all the way up to t equal to 0. We are not going to get that in the table. The table will have start from certain low pressure, so we have to at least get that. The lowest pressure available in the given table will, that is the level of accuracy we can get. So now, if you look at such a table, so you have to identify the superheated steam tables. Now let me put that down. Those of you who have a copy of the tables, whichever book it is, or whichever format, the units of course are very important. Now the 300, this is 8 megapascal 300, but this is not what I want actually. I want the other one. This is in terms of pressure. 8 megapascal, you can easily see 300 degrees centigrade is superheated. But what I want is actually this, the low pressure. The low pressure, you can now see this is the temperature superheated steam. It's continuous. These temperatures are given. So obviously the temperature we are interested in is 300. Now you see the lowest pressure is 1 kilopascal. Right? Lowest pressure is 1 kilopascal. So let me write that down. The pressure 1 kilopascal. And then I have to look at V. This is V is in centimeter cube per gram, I think. It might be there at the bottom of the table. But anyway, let's see what the V here is. 264500 corresponding to 300. Right? I'll write that down also. 2645 in centimeter cube per gram. 2645 and only 20. This is what is the specific volume. Now you go to other 10 kilopascal, that's the next value that's given. So again, I focus on this, I get 26440. So I will considerably decrease, and then 30 to 10 and so on. So you have to collect all these data and record the value of V and subtract it from the corresponding RT by V, and then you have to numerically integrate it. So what you are getting, right? So first, what you have to construct is first the table of V, and it has to extend. But if you see this page, the last value is about 100 kilopascal. You see far away from 8 megapascal, right? 100 kilopascal is 0.1 megapascal. So this is far away. These tables will run. If you are tired of noting each one of these values, you can take it at a slightly longer interval. But you have to go all the way up to P equal to 8 megapascal, and that I have the values in this table. Probably this is the superheated steam. You can see how much it would have reduced. Here, 300 degrees centigrade. Here you can see the units are clearly written it down. It is 24264. The value right on top. 24.264 actually. So this is 8000 kilopascal, which is 8 megapascal. Then I am looking at 300 degrees centigrade. These are the values versus specific volume, specific internal energy, specific enthalpy, and specific entropy. 24.264 is the specific volume. It is reduced by orders of magnitude. Per gram looks better. Right, so now I have to also calculate This is a comma or a dot. It looks like a dot. So we leave it at that. So now I also have to calculate RT by P because I have to subtract at each pressure, right? But now you will see that units become very important, right? Because this is in centimeter cube per gram. First I want to convert it to meter cube because I don't want to read centimeters. Right? Meter cube, and still so meter cube means into 10 power minus 6. Right? And I further don't want in gram, but rather I will do it in gram mole because for gas, especially RT by P is directly in terms of mole. Otherwise, I have to calculate the R in terms of per gram for water. Right? So this is so make it meter cube per gram. So if I want meter cube per gram more, what else I have to do? Yeah, so multiply or divide by 80. Multiply by 80. Right? So now in terms of meter cube per mole, can you tell me what this is? So this is 0.2645 times 80. That's all. Okay, meter cube per mole. That seems reasonable, right? Now let's calculate RT by P. RT by P would be 8.314 times 300 centigrade. So I have to convert it 573 divided by the pressure is now 1 kilopascal, not 8 megapascal, because we are still at the lowest pressure. So 1 kilopascal is 1 times 10 power 3 pascal. And that's what I want. What is the value I get? The ideal gas. Huh? Something doesn't seem to be closer. Anyway. Huh? How come you are not able to calculate even this number? Yes. 4 point? Yeah. I would take that because 76? 39. Okay, whatever. You can see it's almost close to each other. We expect that 1 kilopascal. Now you can easily calculate 24.264 times 10 power minus 6 times 18 at 8 megapascal. And here 8.314 times 573. Now by 8 megapascal will be 8 times 10 power 6. So what are these values? You will see a distinct change in the difference between V and RT by P. That is at the heart of the fugacity. This is one way of looking at the fugacity. Not so much in terms of the energy functions, but rather in terms of the volume and an integral of that. So how much is this? 24.264 times 18 times 10 power minus 6. 4.37 times 10 power minus 4. And what is this? 5.95 times 10 power minus 4. So you can see the difference is definitely, here it's almost the same, here it is quite a bit different because it moved from the low pressure ideal gas tail and it's now reaching. And one thing you can also see, this is slightly larger, V minus RT by P, you can see throughout negative, V minus RT by P. So you can expect the integral to be positive or negative? negative, right? Because if the integrand is throughout the range, a negative function has negative values throughout the range. If it oscillates, then you cannot say it will be 0 finally. But certainly since P minus RT by P is negative, starting from the lowest pressure to the highest pressure we want, you can easily expect that this integral is going to be negative. What does this say about the fugacity at 8 megapascal? RT logarithm F over P. So what can you say about the fugacity? Will it be greater than or less than 8 megapascal? Huh? Less than, right? If we quick with these answers, it's going to be less than. As indicated, we have said the fugacity equals the pressure in the ideal gas range. You can now see that the ratio of fugacity to pressure, the fugacity coefficient will give a measure of how far we are moving from the ideal gas. It's going to be less, that's very clear from the values. Without even calculating the integral, I can say it's going to be less. Right? How much it will be less, for that you have to do the calculation. They will do it numerically. You've got discrete values, you can use any of the numerical formula and calculate it roughly. That's not what we are going to do. Other than the energetic data, clearly he is referring to directly getting. This is obviously G minus GIG at T1, T1. And if you look at the tables, you are given basically B is given. We are not going to need that now really. U, H and S are given. Either S and H or U and S can be used to find G, which is what we need, right? So if you look at this, here we can write down the values right here, because this corresponds to, because this is now all going to be at 300 degrees centigrade and 8 megapascal. That's what I have. So let's write it down. H is 2759.9. So I now write it. H at 300 degrees centigrade, 8 megapascal is 2786.8 kilojoule per kilogram. That's the unit. And S, this is all, even though it's capital S here, it's all specific entropy. It is 5.7471. 5.7471 kilojoule per kilogram per Kelvin. That's yes, that's given right from the tables. So I can calculate now G. How do you calculate G at 300 degrees centigrade and 8 megapascal? H minus PS. So G at 300 degrees centigrade, 8 megapascal is H2786.8 minus T would be 300, 573.15 times 5.7471. I mean, units are very important. So it is kilojoule per kilogram only. You may have to convert it to per mole later on. Right now, I can leave it at this. So you can calculate this and keep it ready. Now the whole point is, so this is very easy to calculate. How do I calculate? This also easy if you calculate from the table. GIG, the ideal gas, because the steam tables give only the water property, not the ideal gas water. Because the ideal gas doesn't have any liquid or anything. It's all gas flow, right? Or solid. It doesn't become anything other than gas, right? So how do you get GIG for water from the tables? He says you have to get. Is it possible to get it or not? For low pressure you are saying, okay, let's take that, we put that low pressure table back. Lowest pressure will go and look at what it gives. Okay, the lowest pressure is 1 kilopascal, right? So now at 300, that is very important. Temperature you have to keep in mind. Temperature is always 300. Since ideal gas refers to the low pressure behavior, so I am calculating here. I write down the H here at 573.15. H is 3076.8, right? So 1 kilopascal. Alright, in another color. So 3076.8. This is now at 1 kilopascal, kilojoule per kilogram. Now, S, the value of S at 300 degrees centigrade at 1 is 10.3450. 10.3450. Now, if I calculate the G as right 3076.8 minus again 573.15 times 10.3450, will that give me this quantity GIG at 300 degrees centigrade at 8 megapascal or not? This is now crucial. It will help you, it will test your understanding of the ideal gas properties. I calculated upon, she said, low pressure you have to go to. So I went to the lowest pressure that's available, 1 kilopascal, right? 1 kilopascal. I calculated the G at that point, right? But that is but what I want is G at 300 degrees centigrade 8 megapascal minus GIG at 300 degrees centigrade and 8 megapascal. So first you answer the question whether the answer that I have here will that give me this or not? Yes or no? But you two answers I want. One of the it won't. Why? What I want is at 8 megapascal, right? GIG. But what I have got is at only 1 kilopascal, because the G for the ideal gas is a function of both temperature and pressure. Because enthalpy, then I can take this to be the ideal gas enthalpy. But the G as well as S we saw, and also A, even the ideal gas properties depend on both temperature and pressure. So what I want is different from what I have. So let us first write what I have, right? So let me now rewrite this slightly. And now we have through the thing. So what I want, that's why it's very important to the arguments. It's just not some G and some GIG. The arguments are very important. What temperature and pressure or what temperature and volume. So what I want is G at 300 degrees centigrade 8 megapascal minus GIG at 300 degrees centigrade and 8 megapascal. Obviously the two are different. If C B minus RT by B to calculate is going to be not equal to 1. F over B is not going to be equal to 1. So what I have, this is what I want. What I have now so far from the calculations is G at 300 degrees centigrade 8 megapascal, because I won't even write, minus G at 300 degrees centigrade and 1 kilopascal. Now this is approximately, this is the actual, because the table doesn't give the ideal gas, refer to the ideal gas. However, this is sufficiently low pressure, and I assume that the properties of the actual water will approximate its ideal gas properties. I can write this also as GIG. But how do I get this difference? Gibbs free energy. Right? So how do we get this difference? So I now write it slightly differently. Right? So I write it as G at 300 degrees centigrade, 8 megapascal, minus GIP is what I want. But what I have is minus G at 300 degrees centigrade and 1 kilopascal. And I know that, so I have got this. This is directly available from the tables. Now I know that G at 300 degrees 1 kilopascal is approximately equal to GIG at 300 degrees centigrade 1 kilopascal. At the same pressures they are equal. So I write that plus what do I have? I have this. I have written it. Now I have written two terms, one negative, one positive. The two are approximately equal. So effectively I have added only 0. Approximately I have added 0. So it's not going to make any difference. But I am still left with this. So I have to subtract that. Now can you tell me this? So I have got this. This I have got from the tables, right? Now what about this? Do I need the tables to get this? Or what is it equal to? It is GIG at the same temperature, right? Two different pressures. So it has to be an integral of dGIG by dP between the two pressures. So I can clearly write this difference. I am going to put within flower brackets as integral. The negative is in the 8 megapascal, so it will be 8 megapascal to 1 kilopascal, right? 1 kilopascal. RT dG by dP for the ideal gas is RT by P. RT1, which is 300 Kelvin by dP. So it's nothing but 8.314 times 573.15 times the logarithm of 1 kilopascal. With ratio is very good. It's going to be again a negative quantity. 1 into 10 power 3 by 8 into 10 power 6. So I have now split what I want into two parts. One part I get from the tables directly. The second part, which deals only with the ideal gas property, I can directly get it from the property of the ideal gas, namely the derivative of G with respect to P I know. So I can get that. Of course, the crucial point I am making here is the fact that the value I have got at 1 kilopascal, why that is also important, as you can see. Even though that doesn't correspond to GIG 300 degrees centigrade 8 megapascal, that's very crucial to complete the problem. Right? So I'm adding and subtracting two terms which are almost equal to each other. So I'm now expressing effectively the difference that I want in terms of two differences, one which I can directly calculate from the tables and one other which I just calculate using an integral, using a property of the ideal gas. So if you put all these things together, I'll just write down, it will be a good exercise for you to put everything together and calculate the final answer, which I will just write. It's there in standard, and you can also repeat the same thing for the answer. The Fugacity is approximately, for all these calculations, you should be able to show that it is approximately equal to 6.36.
Yes, it is
6.36 megapascal. You should be able to calculate it. So what I do is calculate the difference from the tables. I've already calculated what I want from the tables here. I put that on the board. You can go and verify that. And I have that other integral corresponding to the ideal gas I've written it. So you have to plug the two together. All you get is RT1 logarithm F over P. So T1 is 300 degrees centigrade. P there is 8 megapascal. So you can calculate F from that. Right? So now the next question standard has is calculate the saturation fugacity. Now the saturation fugacity proceeds in the same way. Only I want, instead of the values at 8 megapascal, obviously I want at 8.6 megapascal. If I wanted to use P minus RT by P, I have to further go down all the way to 8.6 megapascal, but I am not going to do that because that involves integral and recording so many B, but this is more direct. So it's very straightforward. The lower pressure, those remain the same, but instead of 8, I need the data at 8.6, the saturation. So you can calculate the saturation fugacity. And that turns out to be, I hope these answers are here. Saturation fugacity turns out to be 6.7 megapascal. So even if the fugacity has increased, what is crucial is to look at F over P. You will see that F over P has slightly further reduced when you come to, because this has been divided by 8.6, because this is divided by 8. The fugacity is going on increasing. You look at it in terms of the integral, further and further you are integrating down, right? So the fugacity is increasing in terms of units, pressure units, it is increasing. That should not be a big surprise, but it's the ratio F over P, right? That should decrease because the integral is becoming more and more negative. So you look at it from B minus RT by B integral, right? So you calculate phi, you will find that phi at this is less than phi sat. Now we don't have time for the third part of the problem. Then Sandler says, so one is, second is saturated, P sat all at 300 degrees centigrade, 8.6 roughly. The third one is P equal to 25 megapascal. To what state does that correspond to? 25 megapascal. Liquid, right? So, how to calculate the fugacity of the liquid from the tables? Now, for that, we need something called as the Poynting correction factor, which you might have all heard of. Right? Poynting correction factor helps you to estimate the fugacity of a subcooled liquid from the saturation fugacity. So, we need to know the saturation fugacity, which we will be able to calculate from the tables. Then the question is, certain unique properties of the liquid phase which we make use of to simplify the calculation of the fugacity in the liquid, because you will see none of the tables will usually have data in the subcooled region. You won't be able to get those. Otherwise, the problem can proceed in the similar way, right? But you won't get any data that is there in the subcooled region. So what we do is we use the saturation fugacity, which we can use get using the tables, right, and then try to approximate the calculation of the subcooled fugacity. Are there any questions before we wind up for today? So we'll complete the discussion with the subcooled liquid, and then we will continue, finish the assignment on Monday and go on to the next topic, which will be mixtures, right? So we'll end at this